So far, we've introduced mathematical vectors. Vectors, at least in the sense we think of vectors when we write them as columns or rows of numbers. Of course, the idea of a vector suggests, at least informally, the idea of some space, perhaps analogous in some way to ordinary geometrical space, in which we have ordinary geometrical vectors. In fact, we can think of these new vectors as being in some space, and it's actually rather important mathematically that we define the properties of this space. We're going to find that it has much in common with our ideas of geometrical space, which means that, at least loosely, we can visualize much of the mathematics by analogy back to our ideas of ordinary geometrical space, or what we sometimes call Cartesian space. We can't take this analogy very rigorously for two reasons. First, our mathematical space here may have a different number of dimensions. This could be fewer than 3. For example, the mathematical space to describe electron spin has only 2 dimensions. Or it could be more than 3 dimensions. In fact, it could even have an infinite number of dimensions. The second difference is that in the space that we need for representing our quantum mechanical vectors, we have to allow complex numbers as the projections of some vector along an axis. Ordinary geometrical space only has real numbers for the projections of a vector along an axis. However, these differences need not prevent us from informally thinking of our new vectors as being, in many ways, similar to our existing ideas of geometrical vectors. And this can be a useful way to visualize quantum mechanical states. One that will remain informally useful as we work with systems well beyond the simple functions we've been discussing so far. Our new space, incidentally, rather than being called a geometrical space, will be called a Hilbert space. We will start to discuss all of these ideas in more detail now.
So we need a space then in which our vectors can exist. For a vector that had 3 components, a1, a2, and a3, then we could imagine a simple 3-dimensional Cartesian space. The vector can be visualized as a line, just like drawing a vector as we're used to doing. And it would start at the origin, and it would have projected lengths, a1 along the x direction, a2 along the y direction, and a3 along the z direction, along these axes. And of course, each of these axes, x, y, and z, these axes, are at right angles to one another. For a function expressed as its value at a set of points, then instead of just 3 axes labelled x, y, and z, we might have an infinite number of orthogonal axes, and they would be labelled with their associated basis functions. For example, the basis function psi n, where that's some particular basis function. Just as we label our axes in conventional space with unit vectors, for example, our notation that we could use here might be that this x hat is a unit vector in the x direction, y hat is a unit vector in the y direction, and z hat is a unit vector in the z direction. Then, in our space here, we're going to label our axes with the ket vectors, psi n. So maybe one of them is psi 1, another is psi 2, and so on. Either notation is acceptable for talking about the spaces, either this one or the one with the kets here. Now, a very important point is this idea of an inner product. And geometrical space has the vector dot product. That defines both the orthogonality of the axes. So if 2 axes are orthogonal, then x, the unit vector along one of them, dot y, the unit vector along the other, is 0. So for 2 vectors that are non-zero themselves but have a 0 dot product, we say they are orthogonal. And the components of a vector along these axes are also defined using the dot product. So if we have a vector f, then we have components fx along the x direction, fy along the y direction, and fz along the z direction. Then the component fx is simply the dot product of f with the unit vector along that particular axis. And similarly for the other components. For finding these fy's and fz's, they're done with the dot product. Now, our vector space here that we're going to use for our functions has an inner product that also defines both the orthogonality of the basis functions. So here would be the condition for orthogonality. This is our inner product of this bra vector, psi m, with this ket vector, psi n. Because these are an orthonormal basis, then this is 1 if n is equal to m, and 0 otherwise. So that's the Kronecker delta here. So our vector space is using this inner product to define the idea of orthogonality, and it also defines the components for us. So the specific expansion coefficient Cm is simply the inner product of the bra vector psi m with the function f in our expansion, where these are the expansion coefficients. So now let's look at the mathematical properties of our space compared to the geometrical vector space. For example, we can start by looking at addition of vectors. Well, with respect to addition of vectors, both geometrical space and our vector space are commutative. That is, the two vectors a plus b added up in that order give us the same thing as the two vectors added up in the other order, b plus a. That's a normal property of vectors in geometrical space. Similarly here, if we add two ket vectors, it doesn't matter what order we add them in. And both of these are associative. If we are adding three vectors, it doesn't matter if we add b plus c first and then add a to the result of that, or if we add a plus b first and then add c to the result of that. And similarly here, if we had three ket vectors, f, g, and h, it doesn't matter if we add g and h first before we add f to them. And similarly, we could add f plus g first and then add h to that. Both of these spaces are linear. So they're linear in multiplying by constants. So a constant number multiplying the sum of these two vectors is the same as that constant multiplying this first vector plus that constant multiplying this second vector. So that's one of our linearity criteria. And similarly here in our new space, multiplying the sum of these two vectors, these ket vectors f and g, by some number c, is the same thing as multiplying the vectors individually, f multiplied by c plus g multiplied by c. And one subtlety here is that our constants c are going to be allowed to be complex numbers, not just real ones. And our inner product is linear, both in multiplying by constants. So here is a dot product into c times b. That's the same thing as c into a dot b. And similarly with our bras and kets in our new space, the inner product of f with the ket vector c times g is the same thing as c times the inner product of f with g. And in superposition, so a dot b plus c is the same thing as a dot b plus a dot c. And in our case with the bras and kets, f inner producted with the sum of g plus h is the same thing as the sum of the inner products, f inner producted with g and f inner producted with h. There is a well-defined length to the vector, and that turns out to be a rather important concept that we must have in our space. So in ordinary geometrical space, this length, or what we sometimes call a norm, is just the square root of the dot product of the vector with itself. Sometimes in mathematics that's indicated with this double-lined notation. Similarly here, we have the inner product of the vector with itself. We take the square root of that to get the norm of f. This may seem an obvious property, but it's very important in a vector space like the one we have that it has an idea of length in it. Because the idea of length means we know how far something is from something else. For example, if we're trying to find an approximation to some function, we need to know formally how close we might be to the right answer. and we need to be able to define that as some sort of distance or norm. That's critical for most of the underlying mathematical proofs of how these spaces work. Now, a very important concept that we've already discussed is the idea of completeness, and in both cases of both our spaces here, any vector in the space can be represented to an arbitrary degree of accuracy as a linear combination of the basis vectors. This is the idea of completeness, as I said, of the basis set. In vector spaces, this property of the vector space itself is sometimes described as compactness. This idea of compactness is one that has several slightly different uses in the formal mathematics of vector spaces, and we won't end up discussing it in much more detail, but this term does occur. In geometrical space, the lengths ax, ay, and az of a vector's components are real, so the inner product of the vector dot product in this case is commutative. A dot b is equal to b dot a. But with complex coefficients rather than real lengths, we choose a non-commutative inner product in the following sense. The inner product of f with g is going to be the complex conjugate of the inner product of g with f. So in that sense, the inner product is not commutative. The inner product of f and g is not equal to the inner product of g and f. It's equal to the complex conjugate of it. So that's the first important and somewhat significant difference between our vector space and the ordinary geometrical vector space, and it's a consequence of the fact that we want to be able to work with complex numbers. This relation turns out to be a very important and useful one. For example, it ensures that the inner product of f with itself has to be real, because it has to equal its own complex conjugate. So even if we're working with complex numbers, this inner product of f with itself is always a real number because of this property of the inner product. And the fact that it is real means it can be used to form a useful norm. So a mathematician in constructing this space might say, let's construct a space like this where we make the inner product, when we flip it round, be a complex conjugate. That means that we get all these nice mathematical properties in our space. And of course, this space is going to turn out to be a very good one to represent all of our quantum mechanics.
The elementary mathematical properties above, other than the inner product, are sufficient to define these two spaces as linear vector spaces. Mathematically, our vector space can also be called a function space. A vector in this space is a representation of a function. The set of basis vectors, or basis functions, that can be used to represent vectors in this space is said in linear algebra to span the space. With the added properties of the inner product, these are what are called Hilbert spaces. The Hilbert space is the space in which the vector representation of the function exists, just as normal Cartesian geometrical space is a space in which a geometrical vector exists. The main differences between our vector space and geometrical space are, first of all, our components can be complex numbers rather than only real ones. Second, we can have more dimensions, possibly an infinite number. Third, because we are working with complex numbers, our definition of inner product has to be slightly different from the vector dot product that is the inner product in ordinary geometrical space. However, that inner product still helps us define the idea of orthogonality. If the vector dot product of two non-zero vectors in a geometrical space is 0, then we say that those vectors are orthogonal, that is, at right angles in that space. Similarly, if our inner product of two non-zero vectors in our vector space is 0, then we will say that those two vectors are also orthogonal. As we said, despite these differences, the idea of a geometrical space is still a useful informal starting point for visualizing our vector space, and we will continue to use that to help us visualize quantum mechanics.